Good day. For my project, I did the Chernobyl Reactor 4 disaster that occurred in Chernobyl or Pripyat, Ukraine, back in 1986. So, what happened at Chernobyl? On the 26th of April, 1986, Reactor 4 at Chernobyl exploded. In this explosion, two people died almost instantly. I believe one was killed in the actual blast, and the other died shortly thereafter in the hospital from injuries sustained. Another 28 staff and first responders died from acute radiation sickness within the next few weeks. Beyond that, we don't know any exact numbers of casualties for Chernobyl. And a big reason for that is the Soviet cover up operation that ensued after the disaster happened. The Soviet Union went to some pretty extensive lengths to cover up the full extent of the disaster. What we do know is that over 68,000 people were displaced due to evacuations, and the Chernobyl exclusion zone was over 2,600 square kilometers in area. And 2,600 square kilometers is obviously a large area, but they actually believe that fallout made it as far north. Fallout was measured as far north as Sweden, which is up in Scandinavia, which is a very long ways away. That was a measured increase in radioactive material that had fallen as a result of the Chernobyl disaster. And it really disrupted a lot of travel all over the world. And the way that I know this is because, I was adopted from South Korea and I was supposed to be coming to the United States in early May of 1986. And they actually delayed my going to the United States for about a month because they were concerned about the potential for fallout from Chernobyl traveling all the way over to East Asia. There's no proof that it ever did, but that sort of highlights the extent and the massive scale of this disaster. And I think sometimes we look at it and we say 30 people is obviously a tragic death toll, but it's not, on the level of some other catastrophes. And that's why I did mention it's important to realize that we don't know the full extent of the casualties from Chernobyl, and we probably never will because of the cover up that followed. So, what caused Chernobyl to happen? We have many nuclear reactors all over the world, and we're told that they are all very, very safe. So, why did reactor 4 explode? And should we be concerned that the nuclear reactors in other parts of the world are going to explode as well? Because obviously, the idea of exploding nuclear reactors all over the place is not particularly comforting to anybody. Well, what caused Chernobyl to happen was really a combination of different factors. And some of these involved reactor design flaws, and most of these were caused by budgetary concerns and lack of investment in new nuclear technologies. There was also the fact that the Soviet nuclear program really prioritized efficiency and production over safety, to the point that safety was treated at times like it was kind of like this distant afterthought, which that's not really good in any job field, but it's especially not good in job fields where you could create a nuclear explosion that wipes out everything within a couple kilometers radius. And the other problem here was really some of the personnel dynamics that were present in the control room when the disaster happened. And we'll go over all of that throughout this presentation. But it's important to realize that Chernobyl was not caused by any one failing. It wasn't like there was bad science involved or incompetence. Neither one of those things was the sole cause. It was sort of this perfect storm of factors that all combine to create this catastrophic explosion. So, before we go into the science and the actual events, we need to understand the history of the Soviet nuclear program. So, the USSR's nuclear program had a bunch of different organizational deficiencies, for lack of a better word. The program was run by the Ministry of Medium Machine Building, which the Soviets called the Ministerstvo Srednjego Mashinostroyenia, which they had understandably abbreviated to Shredmash because nobody was going to say the whole name over and over again, not even a Russian person. Now, the Ministry of Medium Machine Building controlled all aspects of atomic energy in the Soviet Union, and that included both the nuclear weapons program and the civilian power program. So the ministry was also primarily an apparatus of the Communist Party, which ran the Soviet Union, and therefore it was headed primarily by analysts and bureaucrats, not by scientists. And because of this, the ministry was a lot more concerned with meeting production goals, meeting quotas, and efficiency statistics as opposed to good science and safety. The militarized nature of the ministry also meant that the Soviet nuclear program, both civilian and military sides, were very secretive. And this meant that there wasn't a lot of outside influence. The Soviets didn't allow any international inspectors to view their nuclear power plant designs, their procedures, or tour the nuclear power plants at this point because of the fact that many of these plants were RBMK reactors, which were capable of dual purpose in providing electricity and manufacturing plutonium for weapons. It also meant that because the nuclear program, the military side, was so secretive, there was no real internal civilian oversight over nuclear facilities in the Soviet Union. It was run entirely by the ministry, which was sort of this cloistered group that was kind of kept to itself and was very secretive. And this wasn't really unique to Shredmash. This was most organizations in the Soviet Union because in the Soviet Union, there was this intense competition and paranoia between senior members of the government. And so each minister would try to keep his department as cloistered, internal, and loyal to him only as possible, because that was kind of how you built your power base and protected yourself. And this caused problems in a lot of other areas of the Soviet Union, but Shredmesh was no exception to this rule. And so really, this is sort of highlighted in the way that Soviet scientists and technicians were treated. They lived in these cloistered, they were called quote unquote ideal towns. Pripyat was the town that the workers for the Chernobyl plant were housed in. And these ideal towns were called ideal towns because the scientists and the technicians there had access to better houses, better food, better entertainment. You could argue a little bit more freedom than the average Soviet citizen. So they were, these ideal towns were very good places to live, probably the best places that a regular person could hope to live in the Soviet Union. However, obviously remaining in the ideal town required you to remain part of the nuclear program. And because the nuclear program was so secretive, so cloistered, and so built around, the whole Soviet Union really built around these concepts of personal loyalty. Staying within the program and keeping your place in the ideal town required you to not only be good at your job, but also to keep your boss happy. Because most supervisors and managers within the nuclear program were committed and relatively well connected members of the Communist Party. So if you made your boss unhappy, he could get you fired, he could get you kicked out of the ideal town, and in the worst case scenario, he could get you arrested and sent to a labor camp in Siberia. So to kind of put this into perspective for a modern American audience, imagine that you live in a luxury apartment that's provided by your employer. Your employer provides you with good food. They give you a nice, some entertainment, maybe a sports show or a concert that you could go and watch every weekend or every other weekend. That's all provided by your boss. It sounds pretty good, right? But then you also know that if your boss wants, he gets unhappy with you, he could fire you, he can make sure you never get another job again, and he can evict your family from their home, and in the worst case, arrest you and your family and send you all off to a labor camp in the middle of, let's just say, North Dakota, right? So this is kind of a comparable scenario, and I think under those circumstances, most of us would probably do everything we could to make sure the boss was relatively happy. That's kind of basic human nature, because most people prefer living in luxury apartments to living in an abusive labor camp. I think that's pretty easy to agree on. But what this did is these factors all kind of contributed to this organization where safety was less important than meeting performance and efficiency goals. It also led to an environment where following orders and appeasing one's superiors was often more important than following operating procedures and instructions. And these factors played very heavily into what happened at Chernobyl, as we see as we go through the events. Before the other thing we have to understand before we move forward is how a nuclear power plant actually works. So, all nuclear power plants anywhere in the world have these four key features. The first is a moderator. So, what the moderator does is it slows down fast neutrons because neutrons normally will move at a very, very high rate of speed. And when they're moving at this high rate of speed, they're not efficient in colliding and splitting other atoms. And that means that basically, if you have only fast neutrons, your fission process is going to fizzle out because there's not going to be enough collisions to sustain it. So, moderators slow down fast neutrons into thermal neutrons, and thermal neutrons are much better at colliding with and splitting off additional neutrons from other atoms. And this is what creates a sustainable fission process. Moderators in the Soviet reactors, as we'll see, were made out of graphite. So another feature that all nuclear power plants have is an absorber. And these are control rods, usually, and they're made from elements like boron or boron carbide, and they're very good at absorbing neutrons. So basically, when you think about it, if the neutrons are all being absorbed before they can collide, that's basically going to stop your nuclear reaction. That's the purpose of the control rods in the nuclear power plant is to, when you insert the control rods, you decrease the rate of the reaction. When you withdraw the control rods, you increase the rate of the reaction. Another feature that all nuclear power plants have is coolant. Coolant's very important because the nuclear fission process generates a lot of heat. Most reactors, especially in 1986, used water because water, we all know, everybody knows that when water boils, it turns into steam. And we all know that you could use steam to power turbines that then create electrical power. So, on a little side note here, water is actually a very interesting substance when it comes to nuclear power because water is a mild absorber. It can also act as a moderator and it can be a coolant. And this is what most US nuclear reactors use. They use water as the moderator and they use water as the coolant. And this is a very, relatively safe design. We'll cover that a little bit later when we talk about the void coefficient. The last feature that nuclear power plants all have in common is some sort of shielding. This is usually a steel and concrete structure that you build around the reactor. First of all, this helps to keep atmospheric oxygen and other atmospheric gases away from the high temperatures in the reactor because we all know that oxygen can fuel fire, and that's not exactly a good thing in a nuclear reactor. The other thing it does is if there is some sort of malfunction in the reactor and some radiation escapes, the shielding provides a layer of protection that keeps that radiation from, floating off into the atmosphere and contaminating everything downwind or in the general vicinity. US nuclear power plants also usually have a containment shell. The containment shell is an additional structure that's built around the shielding that provides you just with another level of protection in case there's some sort of a disaster or a catastrophe that breaches the shielding. You still have the containment cell that's going to help to keep the radiation in. Critically, the RBMK reactors did not have a containment cell. Another factor it's important to understand is what's called reactor poisoning from xenon-135. And this also plays a role in Chernobyl. So xenon-135 is a neutron-absorbing isotope that is produced by the decay of iodine-135. Now, iodine-135 has a half-life of approximately 6.5 hours. That's important to understand because during steady operations, the fission process burns xenon-135 at relatively the same rate that it's produced. So this creates what's called xenon equilibrium, where you're producing xenon-135, but it's burning off as it's produced, so it's not really a big deal. However, when a reactor reduces power, xenon-135 can build up as I-135 was produced at previous operation levels, but is decaying. And because of that 6.5-hour half-life, it's still decaying as if you're still producing xenon-135 from that decay, as if the reactor was operating at full capacity or whatever capacity you were operating at 6.5 hours previously. This causes xenon 135 to build up. And obviously, when you're having a buildup of a neutron absorbing material, this makes it more difficult to control the reactor as it's powering down. This is called reactor poisoning. Now, this plays a role at Chernobyl, but it's important for us to understand that reactor poisoning, even back in the dark ages of the 1980s, was a very well understood concept, and the engineers and technicians at Chernobyl were aware of it and trained on how to handle it. So, with that being covered, let's talk about some of the specifics of the RBMK reactor. So, the RBMK reactor was based on a military design that was actually based on the original reactors that were used for the Manhattan Project. And this military design was adopted in the Soviet Union because it could produce electricity and also produce plutonium for nuclear weapons. Remember, SHREDMASH was a combination of the military and civilian nuclear program, so it kind of makes sense from an efficiency standpoint. Why not produce your power and your weapons in the same facility? So RBMK reactors used graphite blocks as a moderator and used water as a coolant. And this is kind of inherently dangerous because if the reactor becomes runaway, which means that the reaction is increasing beyond their ability to control it, the increase in heat can cause water to rapidly vaporize into steam. Now, as we have studied throughout the course of the semester, we know that when you convert a liquid into a gas, it takes up more space, which creates more pressure. And pressure explosion is caused when pressure builds up so quickly in a contained space that it explosively decides to leave that contained space. Graphite can also catch fires at extremely high temperatures, such as those in a runaway reactor. And if a steam explosion was to expose the burning graphite to atmospheric oxygen, you could have another combustion explosion that, could obviously cause a lot of problems because in general, you don't want to have a lot of explosions around your nuclear fuel rods for some rather obvious reasons. So RBMK reactors used multiple pressure tubes as well for fuel cells. This is different. A lot of US commercial power plants, they use only one pressure tube for the fuel cells. Now, having multiple pressure tubes increases the complexity of the design and required more water for cooling. However, because you had these individual pressure tubes spread out through the reactor, you could shut down individual sections of the reactor without shutting the whole thing down, and that allowed you to pull out certain fuel cells and extract the plutonium from them. And so this basically allowed the RBMK reactor to produce both plutonium and electricity. You didn't have to shut down the entire plant every time you wanted to extract the plutonium. You just had to shut down the section that you were extracting. So once again, very efficient design, but slight decrease in safety because you have a more complex design that requires more water to cool it. And the last thing is that RBMK reactors, as we discussed earlier, they lack the extra shielding of a containment vessel, which would have provided some additional protection if the reactor's initial shielding was breached. And on the right here, you can kind of see a picture of how an RBMK reactor is set up. All right, so one of the major flaws, and probably the number one most important scientific concept to understand for the Chernobyl disaster, is the concept of void coefficient. So normal water basically acts as a mild absorber, a moderator, and a coolant. We kind of discussed that earlier. When water vaporizes into steam, it creates voids. And that occurs because steam is much less dense and therefore doesn't absorb neutrons as well. And this is what is measured by the void coefficient, because when you have these steam bubbles, they create areas that aren't absorbing neutrons as well, and that obviously can affect your rate of reaction. Now, in reactors that use water as both coolant and a moderator, like the US reactors, the LWR reactors of the time, there's a negative void coefficient. And this is because as water turns into steam, it removes both the absorber and the moderator. Because remember, water is absorbing and moderating. So therefore, if your water all evaporates to steam, you lose the coolant and you lose your absorption, but you also lost your moderator. And as we discussed, if you don't have a moderator, the nuclear reaction is pretty much just going to come to a stop. So in this way, there's a negative feedback loop, whereas if too much water vaporizes into steam, it basically just kills the fission reaction. RBMK reactors have a positive void coefficient, and that's because the water is not the primary moderator, the graphite is the primary moderator. So as water turns into steam, it loses the coolant potential and it removes the neutron absorption. But because the graphite is the primary moderator, the lost water does not significantly affect the rate of moderation, and thus the void coefficient is positive. A positive void coefficient leads to a dangerous positive feedback loop that can cause a runaway reactor where the technicians lose the ability to control the fission reaction. And in this positive feedback loop, the reaction is just going to keep building and building and building because unless you put your control rods in, there's nothing that's going to absorb neutrons and slow it back down. And this is in essence what happens at Chernobyl. We'll go through the events of how this occurred. So another flaw with the RBMK reactors was graphite tips. And graphite tips, that's something that a lot of documentaries latch onto as a major part of the problem. They do play a major role in the disaster. However, it's not as if the Soviet scientists blithely decide, hey, let's tip the control rods with graphite and see if we can blow up a reactor today. It wasn't that at all. What happened was that the Chernobyl control rods were tipped with graphite that they ran in these tight channels that the rods would be withdrawn and inserted through. Now, the graphite provided a moderator that would help to offset the absorbing effect of the water, and thereby the Soviet technicians who designed these RBMK reactors believed that the graphite tips would give the operators more control over the nuclear reaction within the reactor. Now, one thing that is also important to understand is that due to the narrow channels and the need to displace the water that filled them, it would take around 18 seconds or more to fully lower a fully withdrawn control rod. During this process, the graphite moderator tip would displace neutron-absorbing water, creating a potential reactor imbalance because the graphite tip is forcing the water out of that channel and replacing it with moderating graphite. And another big problem was that if you use the mechanical motors to reinsert these control rods, as we said, it would take around 18 seconds for them to fully lower. And 18 seconds may not seem like a lot of time, but as we'll see, nuclear reactions that become runaway can get out of hand incredibly quickly. So before we go into the actual events, it's important to understand the cast of people involved in the Chernobyl disaster. These were people who were either directly related to the events or who were actually in the control room when things happened. So this is just a brief list here, and we'll go into each person in more detail. So the first person we need to understand is Anatoly Dyatlov. And he was the deputy chief engineer at Chernobyl, 55 years old, with extensive experience in the Soviet nuclear program. However, he'd previously been a supervisor at a top-secret military facility. And because of that, he developed certain management styles that were a little bit more acceptable in the military than in the civilian world. First of all, he was a very forceful manager who expected his orders to be obeyed without hesitation or question. He also had a tendency to belittle his subordinates that disagreed with him, and he was very frustrated when he went to Chernobyl, which had a mostly civilian cadre, as opposed to a military installation where everything was run on military terms. And Dyatlov had taken to calling his subordinates, I don't remember the exact Soviet or the exact Russian phrase, but it essentially translates in English into effing goldfish. Which, if your boss calls you an effing goldfish several times a day, kind of creates a less than positive working environment. Dyatlov also had a habit of walking around with a little notebook in which he would write down the names of everybody who displeased him or didn't meet his standards. And these are things that, in the military, we kind of expect to be called unflattering names throughout the course of the day, and most non-commissioned officers do carry a notebook where they write down deficiencies. But it's a lot less common in the civilian world, and this made Dyatlov very difficult to work with for a lot of the plant personnel. And then the fact that he was also a forceful manager and very experienced and senior within the nuclear program gave him a lot of added authority. So nominally on the night of the test, or the night of the disaster, Dyatlov was only there for administrative purposes, and control of the test was in the hands of Akimov. But as we'll see, that didn't exactly work out, and Dyatlov's position and personality really played a large role in that. So the next character involved is Alexander Akimov, who was the fifth shift foreman. He was the one who was supposed to be in charge of everything related to the test that they were conducting that night. He was 32 years old, so significantly younger than Dyatlov, but he was respected as one of the brightest technicians at Chernobyl. However, a lot of witnesses and people have said after the fact that he was known to be adverse to arguing with superiors and had a tendency to cave in under pressure from management. And we'll see how that impacts Chernobyl in a little bit. The third player involved was Leonid Toptunov, who was the fifth shift senior reactor control engineer. Now, Toptunov was only 25 years old and only had 2 to 3 months of experience in his position, so you can make the argument he was still kind of learning the job. And on the night of the disaster, he was manning the control panel for the reactor, which included the rods for the controls for the shutdown and all of the controls for the control rods. So some other people who were involved in the disaster were Yuri Tregrob, who was the fourth shift senior reactor control engineer. He was much more experienced than Toptunov, and he had stayed behind to watch the test, but he wasn't technically working, so therefore he wasn't the one at the controls. And the other person involved was Nikolai Fomin, who was the chief engineer at Chernobyl. And it's important to realize that with this test they ran on Reactor 4, Nikolai Fomin had run a very similar test on Reactor 3 just a couple of years ago. And he was the one who had designed this test because remember, everything in the Soviet nuclear program was very insular. So a lot of times these chief engineers could kind of design their own test procedures, and there wasn't a lot of outside oversight. In fact, when Fomin had conducted the test on Reactor 3, he hadn't bothered to notify anybody above him that they were actually doing the test. And because that test had gone off without incident, he didn't feel a need to change anything in 1986 when they decided to run the same test on Reactor 4. So let's go ahead and talk about this test. So on the night of the disaster, Soviet engineers planned to run a test of the backup electricity for the water pumps that powered the coolant system. And their plan was to power down Reactor 4 and see if the coasting turbines provided enough power to maintain the water pumps until the backup generators came online. Because basically, in the event of a power outage, the plan to power the coolant system for the nuclear reactor was to use backup diesel generators. But these generators took about a minute and a half to come up to full power. And so you had kind of a minute and a half where there wasn't really anything that was going to power the coolant system. So the Soviets rather optimistically said, well, the coasting turbines, they're still moving, they're still generating some electricity, even though, they've been shut off. That should provide enough power to power the coolant system until the backup generators can come online. But this had never actually been tested. It was supposed to be tested in, I think, 1982 or 83 before Reactor 4 went online, but the plant director had waived that test because it was just more expedient to bring the reactor online and start producing power than wait to conduct the test. They had tried to conduct it in subsequent years, but they'd had failures in the testing equipment, and so it hadn't actually been done yet. So this is the first time that they were going to be conducting this test. Now, the plan was to gradually reduce power throughout the day down to about 720 megawatts, with 700 being considered the minimum to conduct the test. And we're going to talk about this in megawatts here because that was the eventual product of the nuclear reaction, and that's what most of the sources use to measure the power production in the reaction within Reactor 4. So it's just basically the easiest numbers for us to get. And we all kind of understand megawatts. It gives us a consistent, easy metric to go off of. But it's important to realize that we're not really talking about electrical production here. We're talking about the rate of the nuclear reaction, which is then sort of demonstrated to us in the electricity that was being put out. So the original plan was for this test to be conducted by the day shift on the 25th. And so only that day shift was briefed, And the overriding view of the reactor technicians was that this was primarily an electrical test, not a test of the reactor. It was seen as being pretty mundane and was expected to take under a minute. Specialist contractors had also been brought in from Donetsk to monitor the electrical readings and to operate the test equipment. And a physicist was supposed to be present to assist if there were any unforeseen reactor problems. However, on the actual day of the test, well, it started off pretty well because just after midnight on the 25th, reactor 4 powered down to about 1600 megawatts, which was roughly half of its capacity. However, in the morning on the 25th, another power station had an unexpected malfunction and went offline, causing the Kiev grid to order reactor 4 to maintain production levels until at least 2100 hours through peak hours. Now, you have to realize that during this time, Soviet factories are trying to meet end of quarter production deadlines, so they needed all of the electricity that they could get, including the 1600 megawatts being produced by reactor 4. Now, by the time they were allowed to power down to the test levels, the specialist contractors from Donetsk were threatening to go home because they'd been told that they would be doing the test just around like afternoon, and it was now past 9 p.m. at night. And the physicists, due to a miscommunication, had been told that the test had already been completed and never bothered to show up. And shortly before the test began, there was another shift change occurring, which brought the fifth shift and the inexperienced Toptunov to the control panel. Fifth shift had not been briefed on the test, and they had not been prepared to run the test. They had only thought they were going to be managing a shutdown reactor, and because they were just coming on to shift, there wasn't really time to bring them up to speed. So, regardless of that, they went ahead and started doing the test. However, before the test began, there was already friction in the control room. Dyatlov wanted to drop the reactor to 200 megawatts, likely because he believed this would be safer. Akimov protested with the procedure book in his hand because he knew that 200 megawatts, the reactor would be much more difficult to manage and significantly less stable. However, Dyatlov asserted that he knew better than the procedure. This was something he'd done several times since he'd started working at Chernobyl. And Akimov eventually allowed himself to be overruled by the superior and ordered Toptunov to decrease power to 200 megawatts. Now, in order to maintain those low power levels, as we just discussed above, it would be more difficult to do so. Toptunov had to switch to a different operating mode called global automatic. And this was sort of like an autopilot for the nuclear reactor. It would basically have computer systems take over a lot of the functions in order to maintain the reactor at a lower power level. However, in order to go to global automatic, Toptunov had to specify a level at which the computer was to maintain the reactor. For whatever reason, he forgot to set this level, and so the computer defaulted to its last known setting, which was about 20 megawatts. And 20 megawatts, we look at it, the capacity of the reactor is 3200, so 20 is basically a shutdown state. And the computer system worked as intended, and the reactor's power dived sharply, decreasing from 720 megawatts to 30 megawatts. And so what we're going to talk about here is disputed. But most accounts state that Dyatlov was absolutely furious about the power drop and ordered Toptunov to fix it by removing control rods. And Toptunov refused because he knew that withdrawing a lot of control rods could cause a dangerously unstable situation in the reactor, but Dyatlov threatened him. And according to Toptunov's account, Dyatlov basically said, if you won't do it, I'll find somebody who will. And because Yuri Traygroup, who was, the fourth shift senior reactor control technician, was standing right there, Toptunov figured that Dyatlov would just have Traygroup carry out his orders. And he was also afraid, Toptunov was afraid, that if he didn't follow orders, he would be kicked out of the nuclear program and kicked out of Pripyat, the ideal town there. And so he just did what Dyatlov told him to do. Now, Dyatlov later would dispute this account, and he would say that he was out of the control room when the power dive occurred, but he could never remember where he went, and he could never remember why he had left the control room. And several other people who were interviewed after the disaster all placed Dyatlov in the control room and more or less substantiate what Toptunov said. And it also kind of fits in with what we know about Dyatlov's personality. So I'm very inclined, and most historians seem to be inclined to believe Toptunov's account of what happened. Now, Toptunov does manage to raise the power to 200 megawatts, but can't get it to raise any more due to reactor poisoning from the neutron-absorbing xenon-135. Now, the way that Toptunov was able to raise the power again was by removing control rods. When he started to do this, he did so unevenly, so he was pulling control rods out of the reactor in an uneven manner. And Trey Group stepped in at this point and asked him basically, like, why are you doing this unevenly? And kind of started to, hold his hand and guide him through the process. Now, this didn't directly contribute to the reactor disaster, but it kind of highlights how inexperienced Toptunov was in his position. And Tregrub and Toptunov basically stood there and removed control rods from the reactor, withdrew control rods from the reactor for about 20 minutes. And ultimately, they withdrew 203 of the 211 control rods. And this managed to stabilize the reactor at just over 200 megawatts of power output. However, to withdraw this many control rods from the reactor was supposed to require consultation with the senior engineer, the actual chief engineer of the plant, who would have been Foman. So there were several reasons for this. First of all, because of that 18-second time to lower the control rods, it was a time-consuming process, and when you reinserted that many of them with those graphite tips, it could lead to an imbalanced and unstable reactor. However, Toptunov and Trey Group were not aware of this safety concern, and they knew that the computer monitoring the control rods of the reactor was often inaccurate, so they just kind of disregarded the regulation. However, with the reactor stabilized at 200 megawatts, Dyatlov ordered the test to begin, and the turbines powered down. The pumps had reduced electricity and water flow decreased, which meant that the water being pumped back in through the coolant system was a lot hotter than it normally was. And this also meant that more steam bubbles formed in the water, and it was at this point that the positive void coefficient started to take effect, and the positive feedback loop began. However, there were no instruments that monitored this or displayed this to the people in the control room, so they had no idea that positive void coefficient was taking hold of the reactor. And we can tell this because the control room at this point, according to witness accounts and recordings, was still very calm. And after about 35 seconds, Akimov announced the test was completed, and he told Toptunov to push the AZ5 button to shut down the reactor. And Toptunov did so and announced to the room that the reactor was shut down. So the AZ5 button started to lower the reactor control rods, which began that slow 18-second descent, displacing the neutron-absorbing water with the moderating graphite tips. What this caused is in the bottom of the reactor, the positive feedback loop spiked, and within 2 to 3 seconds, the entire instrument panel lit up with alarms and warnings. And they know this because Toptunov at that point called out a warning saying power surge, and Akimov yelled this time to shut it down. But by that point, it was too late. And at this point, when Akimov yells to shut it down, Toptunov hit a switch that basically disabled the motors on the control rods and told the control rod it would allow the control rods to drop using the force of gravity, which would speed up the rate at which they dropped. But as we said, it was already too late at that point. Within 3 seconds of the warnings, thermal power had spiked to 100 times the maximum. And at this type of temperatures, the fuel cells ruptured, which spewed superheated contents from the fuel cells, superheated uranium, into the coolant chambers, which basically vaporized what little water remained. The last recording in reactor 4 showed temperatures in excess of 4,650 degrees Celsius. It got hotter, probably, but the instruments were only designed to read that high. So, the subsequent explosion, there are 2 theories regarding what caused it. The first theory is that steam pressure caused the first explosion, and that blew the heavy steel and concrete shell off of the reactor. The graphite then ignited at high temperatures and combusted rapidly with atmospheric oxygen, causing the secondary explosion that tore apart the reactor. The second theory, and this is a more recent theory, is that the second explosion at Chernobyl was actually a small nuclear explosion. And this theory has never been proven, but it is possible when you consider how quickly the reaction increased and the fact that it rapidly exceeded the ability of the instrument panels to monitor it. And we'll probably never know exactly which one of these theories happened, but what we do know is that there were two explosions and reactor 4 was catastrophically torn apart. So, in the aftermath of Chernobyl, tens of thousands of school children were evacuated from the Kiev area and sent to other parts of Ukraine for at least 2 months. The Soviets also covered up the extent of the disaster, and Moscow sent specific instructions to their health minister in Ukraine. And these instructions said that people with, severe acute radiation sickness were to be diagnosed as such. However, those with mild symptoms of radiation sickness, I'm sorry, words are difficult, but those with mild symptoms were to be diagnosed as having vegetative vascular dystonia, a psychological condition with some physical manifestations that closely mimic mild radiation sickness. This is not something that was diagnosed in the West. There are Western diseases that are equivalent, but it was primarily a Soviet medical diagnosis. So basically, what happened is the Soviet Union recognized those that basically died from severe radiation sickness, but didn't bother keeping track of those who had mild radiation sickness, and this allowed them to kind of downplay the disaster a little bit. And this is also why we don't really know how many people's lives were affected by the Chernobyl disaster, because there was this cover up. It's important to note that these cover ups were pretty common within the Soviet atomic program. There had been several other disasters within the program over the last 10 years, and the Soviets had just kind of covered each and every one of them up. So cleanup operations at Chernobyl took months, and that was in large part because the Soviet Union had never envisaged or prepared for a disaster on this scale. Eventually, Dyatlov, Fomin, Brukhanov, who was the plant director, and other senior Soviet leaders were sentenced to various prison terms, with Dyatlov serving 10 years of hard labor and 3 years in prison. Akimov and Toptunov were also charged, but both of them died shortly after the disaster, and so the Soviet government kindly decided not to prosecute them, probably because they were dead. So, the question I think that a lot of people ask when they study Chernobyl is, could this happen again? And the simple answer is yes, it could. The majority of nuclear fission actually happens faster than the human eye can detect. We're talking in the space of nanoseconds. And it releases immense amounts of energy, and that makes it inherently dangerous because we're trying to harness something where we can't see the majority of the reactions, and we're creating a massive amount of power doing it, so that obviously creates a lot of concerns. Now, it is important to note that safety protocols make our nuclear program in the United States significantly safer than the Soviet program, and our reactor design is also a lot safer because we use it's illegal in the US to build a nuclear reactor with a positive void coefficient. So that obviously makes the US commercial nuclear power program a lot safer than the Soviet one was. However, we've had disasters in US history, like 3 Mile Island, and those show us that we are not impervious and kind of remind us that harnessing nuclear power is an inherently dangerous endeavor with catastrophic consequences for failure. And the important thing that we learned from Chernobyl is that these dangers are not scientific alone. They are also dangers in terms of human error and the dynamics that can exist between humans within an organization. And these can happen anywhere unless we constantly reinforce a safety culture. So hopefully, a disaster on the scale of Chernobyl will never happen again, but as long as there is human error, there's always that potential. Thank you for watching this presentation. I hope you enjoyed it and found it informative.